All right, let's get started. Okay, so once the TV decides to pop on, there we go. Okay, so first off, you have a present for me, right? You have homework 7 due today. So go ahead and turn that in up there. So everybody's aware of the homework schedule. I'm giving you homework 8 today. Okay, this might not make might not really matter for you folks that are not in concrete design, but for you folks that are in concrete design, you have a homework due on Monday, and then I'm giving you a homework that's not due to the following Friday. It's not very long homework, but I wouldn't wait until the last minute. I know I'm giving you a lot of time on it. I'm giving you a lot of time on it because the steel homeworks are coming in rapid succession, so it's just something to be aware of so that everybody sort of aware of the big picture. Sound good? Okay. You all have homework 8, which is reasonably sized assignment, I guess. I don't know. It's not huge. There's that. 1, 2, 3, 4, 5, 6, 7, 8. Okay. What's this? You should have one in your backpack. Okay, so homework 8 is on continuously braced beams. What I'll say about homework 8, y'all might want to listen to this. What I'll say about homework 8 is that it's a pretty straightforward assignment. It's going to bring back some topics from way back in the beginning of the semester, though. I was actually going to put live load reduction on the assignment, but I decided not to. The only other thing I guess I'll mention is that you really want to just make sure you're taking your time and paying attention to what's going on with problem 2, because the deflection requirements, just make sure you're dotting all your I's and crossing all your T's with the algebra. That's all I'll say on problem 2. I'm assigning that today. That's due on the 21st, next Friday. After today, you should be equipped to do the whole thing. What? I think did I pass an extra one out on this row? Oh, whoops. The real problem 2. There's another one. There's another one. The first one. I'm sorry. Oh, God. Oh, just wait for homework 9. There'll be 6 problem 1s. There'll be 6 problem 1s. All right, that's due. So sorry about that. That is due next Friday. Sound good? Okay, so let's recap where we left off last time. We were talking about continuously braced beam design, and then I want to spend the rest of the day trying to get as much into the world of lateral torsional buckling as we can. There's a pretty heavy mathematical discussion that goes into LTB, and I'm going to do my best to try and keep it light and keep it straightforward, but there is a lot of math that goes into it, so just be ready for that. Right now, we're on continuously braced beams. We've been working on this example. We were designing a simply supported beam for the following loads. Now, we did the problem for 2 cases. We did case 1. We said, heck with any deflection limits. Let's just ignore deflection limits, and let's see what beam we would select. And we did that one, and we started try and design the beam if we had a live load deflection limit of L over 500, and we ended up stopping because we had the exam in concrete coming up. So that's where we left off. Excuse me. So let me go back here. Okay. Did everybody get a copy of homework 8? Everybody got a copy of homework 8? Okay. All right, so let's make sure we're clear on where we left off with this example. We started off, we had factored moments. We had to assume a self-weight of 100 pounds per foot. We've got our superimposed dead load, superimposed live load. went and factored those accordingly and got a factored moment of 846 foot kips. Now, we also talked about in case 1 about how updating your moments, could that result in a different section, or could it result in a lighter section? Well, it could result in a lighter section. It did not result in a lighter section for this problem, but it did result in a section that was shallower, okay? And just from a constructability and you know, providing room for the architect and what have you, if I had to choose between a W27 by 84 and a W24 by 84, I'd pick the W24. It's just, you know, it gives you more room. So in the end, we went with the W24 by 84. We found that it has just enough moment capacity. Now, I say just enough. Again, let's remember, we took our dead loads, upped them by 20%, live loads, upped them by 60%. We took our capacity and lowered it 10%. I mean, we've got a lot of factors of safety, if you will, built into this. So it's okay that it's, you know, just there. You know, we have a factored moment of 837 and a factored capacity of 840. That's fine because of all those factors of safety built into this. Bless you. Now, we have a FVN of 340 kips, but a factored shear of only about 55. That is not going to be an uncommon finding, and that's okay. We've got phenomenal amounts of shear capacity. Shear's not even a problem. Moment is what governed this design. Okay, everybody okay with this? Everybody good with this? Now let's look at case 2. Okay, now case 2 says, yes? Absolutely. Oh, yes. And the reason why shear capacity is more of an issue in bridges than they are in buildings is because, especially, I'll say especially with bridges that are longer span bridges, we're talking about, you know, past 100 feet, getting into the 120, 130 range, you know, way beyond that. The reason why is because you're not using rolled shapes anymore when you're dealing with spans of that length. You know, you're not using a W27 by 84 or something like that. You're using a customized plate girder. You're actually taking a plate, and actually welding them together. So because you're customizing the girder and tailoring the girder to the specific load demands, what happens is you end up using a web that, for lack of a better term, I'll just go ahead and say it, you end up using a web that's far more flimsy than what you would get in a rolled W shape. So because of that, shear becomes a much bigger deal in bridges. You end up having to put stiffeners and what have you more often than not in bridge elements than you would in building elements. So it becomes a completely different story. For buildings, it's usually never a concern. The only time I would say that shear ever becomes a big concern, or the only common instance where shear becomes a big concern in buildings, is if you have what's called a transfer girder. If you're trying to open up, let's say, a bay in a building, so let's say, you know, let's say here's the floor, you know, and you've got, you know, there's your people. That's about all I got. And you've got, what's that? Thank you. And you've got columns, and you've got, you know, columns, something like that. And you've got, you know, beams framing into it. Let's say what you want to do is you want to, let's say, eliminate the column right here, but you still want it to exist above the second floor. So you would install what's called a transfer girder. And this girder right here is going to be one that's subjected to pretty large shears. So you're going to have some special attention to that girder because it's going to be supporting a fair amount of shear. That's not that uncommon, though, on first floors of large complexes like hotels and things like that. So that's not that uncommon. But in most instances, shear's not a big deal in buildings. That was a long answer, but did that answer your question? That was a good question.
So the roll shapes just don't deep enough for the bridges?
No, it's not that. Well, let me say this, okay? So once you get past, I'd say around 80 feet, maybe a little longer, what ends up happening is you can find rolled shapes that will work, but they end up just being incredibly beefy, like so beefy and so massive that they become uneconomical. They don't become cost competitive. Once you get, once you get past 100 feet, you don't want to be using a rolled beam at all. You want to be using a plate girder because of the cost competitiveness. But because you're an engineer, because you're in design mode, you're wanting to shave as much feasible weight as you can off the girder in order to make it cost competitive. So because you're in that mindset and because that's one of your goals in design, one of the trade-offs is your flanges and your webs are a little more slender than they would be in a rolled shape. So it's all about just checking that and making sure all of your limits are met. Does that sort of answer your question? Yeah, but once you get past 100 feet, I mean, the sections get, ridiculously massive. You can see the span to weight tables, and they just go through the chart. So, sound good? Anything else? This is good stuff.
How to, like you were saying, how you put different plates and put them together. How would you know what,
That's a great question. and here's the best answer. And I teach bridge engineering, and this is how we go about it. When I teach bridge engineering, one of the big tasks throughout the semester, and it's basically one big design project, is to build this super duper massive Microsoft Excel spreadsheet. And basically, based on given input dimensions, it does all of your checks. Okay? So you would, here's essentially how it works. You use guesses and rules of thumb to come up with a trial size, check it. If it doesn't work, make your flanges bigger and make your web deeper, etc. If it does work and it works too well, then thin it up a little bit. And that's basically the long and short of it. It's just an iterative process. How do you get your starting rules or starting sizes? Rules of thumb. I wish I had a better answer for you, but there really isn't. There have been folks that have derived equations that you can use to come up with starting sizes, and they work pretty well, but I don't know that they're I don't know that they have some significant advantage over just, I know that bridge is 90 foot long, take L over 30, and that's about how, deep this element needs to be, and just go from there. So, yeah. Any other questions? Any other questions? All right. So back on to this example. So we need to size this element to withstand a maximum live load deflection of L over 500. Now, algebraically, I'm just going to tell you, this is probably going to get, I don't want to say a little messier, but it's going to get a little more involved than you probably thought it would, and especially on the real problem too on this homework. But let's just treat this mathematically, okay? So this statement is basically saying that the live load deflection must be less than or equal to L over 500, okay? Now, I have a simply supported beam with a uniformly distributed live load. What is the live load deflection? Like, how would I compute it? What? No. This isn't concrete. We're not worried about that in here. Oh, we've talked about that. Yes? Right? Now, just so we're clear, you got that from table 323. Which case, or which figure?
the one.
Case 1, right? All right, sound good? Now, this has to be less than or equal to L over 500. Now, if you're in design mode, what don't you know? If you're in design mode, you don't know what section you're using. You don't know the moment of inertia, okay? So if I multiply the moment of inertia over here on the right and get something like 5W L to the 4th over, let's say, 384E has got to be less than or equal to L over 500, we'll say IX. See what I did there? Now we're going to flip and multiply, right? So I propose that the IX, or I guess IX min, has got to equal 5W I can do better than that. W L to the fourth over 384E times 500 over L. Y'all see how I did that? Y'all see how I did that? Just flip and multiply. Now, one thing, that was easy. The one on the homework is a tad more involved. Okay, there's a little more algebra with it, so just be ready for that. Okay. Now, I'm going to simplify this by saying it's 2,500 W L to the what? Third, there we go. Divided by 384E. See that? So plug and chug, and I get 2,500. Now, our distributed load, actually maybe we ought to put that up here. First off, how long was our beam? Or 720 inches, right? Now our live load, what was it? 0.8 kips per foot. How many kips per inch? Do I multiply by 12 or divide by 12? Divide by 12. You got so many kips per foot, it's only that many kips per inch, so you're dividing. Say it again, 0.067, something like that? Okay. So when I plug in down here, I say 0.067 kips per inch times 720 inches to the third. Now you see where I'm doing that, or how I'm doing that. So 384 times 29,000 KSI. Now, first, now for those of you who aren't using your calculators right now, what should the units be? Inches to the fourth. So let's see if that works out. Let's just do a little quick check down here below this. So what do I have? I have kips per inch times inches to the third divided by kips per inches squared. So that's kips times inches squared divided by kips divided by inches squared. So what? Flip and multiply? So that's kips times inches squared over kips. Starting to look like inches to the fourth to me, right? Funny how all that stuff works out, isn't it? I haven't done that in a while. Wow. Well, just wait. There will be some mind-blowing stuff later. I still have a few tricks up my sleeve. What do we got for this? 5614. Do I have a second on that? We'll just go with that. That's fine. Okay, 5614 inches to the fourth. Okay? Now, let's go back to case 1, for instance. What was the section that we used? All right. What is the moment of inertia for a W24 by 84? Would that section have worked for case 2? Nope. All right. Okay. So how would I select a section based on moments of inertia? What table do I use? Not the ZX table, the one right in front of the ZX table, the IX tables. So So let's go to table 3-3, and I want somebody to tell me the first section that will work. Come on. A W33 by 118. Hey, how's it going?
I've never forgotten line before.
How's it going?
You can't forget your book if you don't come to class.
I didn't say anything. Didn't say anything. Now, what you said a W33 by 118? Okay, what page are you on? 328. Okay, I want everybody to make sure that they're following along with this. So we're on page 3-28, okay, and you've picked the W33 by 118. So you're picking the bold member in that group, right? How's it going? All right, all right. Does everybody see where we're getting that member? Okay, we're on page 3-23. The 33 by 118? Okay, now, that member has adequate stiffness, okay? So we'll say try a W33 by 118. And we selected that based on its moment of inertia of 5,900. I thought somebody said 900. 5,900 inches to the fourth. All right, I'm going to move this up. What happened there? Okay, now let me ask you this. Do we know that that member has adequate strength? So let's go check that. And where do we go to check that? Table 3.2. So go to table 3.2 and look up the capacity counts. I want to look up the phi-mn and the phi-vn. Now, in order to do this accurately, I want to go back to the previous panel. I want to look at something. All right, I want everybody to watch this for a second. I want everybody to pay attention up here. You see this MU value of 846 right there? Okay, when we calculated that value, what was our beam weight? 100. When we updated it, it was 837, and it went down to 84. I want you to keep that scale of numbers in your head. Okay. Now, what is the flexural capacity of a W33 by 118? 1560, about double that. Technically, should we update our moments? Technically. Yeah, we should, because our beam, we assumed 100 pounds per foot. Hold on for a second. We assumed 100 pounds per foot, and our beam actually weighs 118. So technically, we should update that. But I want you all to really sort of recognize the scale. Our moments with 100 pounds per foot are only 846. We just looked up a section that has, what, about double that? Do we really need to? I think we're good. What? Okay, that's a good question. All right, let me, what page are we on so I can follow along? 3-22. Okay. Shape does not meet the H/TW limit for shear, and where it says phi is 0.9. Okay, two answers to that. Number one, we haven't talked about shear yet, so for now, I'm going to say for right now, ignore that. Okay. However, this is one of those limits where it does not mean that if you put a feather on the beam, it explodes. Okay. All it means is that you are using a different specification. Okay. Without delving too far into the realm of shear, what I will say is this. Okay. Shear is going to be a function of how slender your web is. Okay. And one of the limits in terms of what your capacity is is based off of H over TW, your web slenderness. Makes sense since we're talking about shear. Okay? Dependent upon your web slenderness, your phi value actually changes. It's either 1 or 0.9. Okay? For this particular section, all that means is that phi is 0.9. It does not mean that if you place a feather on the beam, it explodes. Okay? And I'm not saying that to be facetious. I'm just making a point. We've had, discussion about those types of limits before. This is just another one of those types of limits. If you fail it, doesn't mean that the section's no good. It just means you would need to use a different section of the spec. We will talk about shear and specifically how the math works at the very, very end. Okay? That limit is taken into account in the table. What is the shear capacity for this section? 489 kips, as opposed to a load of about 50 kips. I think it's good. I'm being silly, but I'm trying to make the point though. Okay.
Yeah, so all it's telling me is that instead of, it's going to use the 0.9, and that's included in that 489.
That's it. That's it. Instead of using a phi of 1, you're using a phi of 0.9, and that is it.
It's already included.
It's already included, yep. Yep. There's only a handful of sections that even matters about anyways. Of all the sections in the spec, there's only a handful of them. So, sound good? So here's how I want to end this problem going over here. So I'll say for a W33 by 118, phi MP was what again? 1560? And phi VN was what again? 489? Is that what you said? 489. So what I'm going to say is by observation, bless you, this shape is adequate. Bless you. Okay. Does this make sense? I really want this to make sense because if you understand this, this is homework 8. So. Everybody good?
What are these other values on this table? MRX?
We're getting to that. That comes with beam buckling. We're going to start to delve into that today. We won't fully explain it today, but we will probably by Monday. So the same thing with the beam factors and LP and LR. So it actually, but to answer your specific question, phi MR is a reduced yield moment. So basically, it's just 70% of the yield moment, and you'll see why we use that here in a second. So, we'll get to it. Okay. Any questions on this? Okay. Well, if you understand this, then you should be good for homework 8. Okay. So, if that's the case, then let's get into, I guess, what would be the best way of describing it as our real final topic of the semester, and that's discretely braced beams. Okay? So up until now, we've been talking about beams, and we've been assuming that they've been continuously braced. Okay? And the reason we've been assuming continuous bracing is because we wanted to eliminate the buckling aspect of beams. Okay? We wanted to just say, let's just not talk about that. Let's deal with continuously braced beams. But the facts are beams buckle. Okay? Now, why do beams buckle? Well, if you bend a beam, a portion of the beam is in tension, but a portion of the beam is also in compression. Okay? And when anything is in compression, it tends to want to buckle. So up until now, we really haven't considered stability. We haven't considered that at all. Okay? We've just assumed that they'll always reach MP, that MP is the capacity, and then that's it. But that's not the case all the time. If I have a beam, something like this, a simply supported beam, and I apply a uniform moment to it, the compression flange wants to buckle, and the tension flange doesn't. Okay? And this is something a little different than what we saw in columns. See, with beams, there's sort of an internal conflict within the beam, because some of the beam wants to buckle, some of it doesn't. Okay? So the way that the beam resolves this conflict of stress is it sort of kicks out and twists. Okay? And this phenomenon is what's called lateral torsional buckling, because it kicks out laterally and twists torsionally. So that, creative name, I know. But it's called LTB, lateral torsional buckling. Okay? Here's some examples of what it looks like. So, for instance, you can see there's just some I-beam that's clamped onto a small little frame, and they've got a really, really light weight on it, but you can see what's happening to the I-beam. It's just sort of rolling over and twisting. There's sort of that LTB effect. This is from a lab test that was done at Purdue. This is actually my PhD advisor at WVU. This was one of his tests for his PhD dissertation. And you can see that they've got this large plate girder, and they're loading it and bending. And you can see it's kicking out and twisting there between those cross frame elements. We've also got some local buckling going on in the flange as well. You can see how the flange is sort of dipping in over here on the right. Those buckling modes tend to go hand in hand. They usually both tend to happen. It's usually more of a question of which one happens first. In this case, the LTB happened before the flange buckle. So, everybody good with that? Okay. Now, in order to talk about lateral torsional buckling, I think it would behoove us to spend a little bit of time talking about torsion, okay? Because it obviously matters. Now, a couple notes before we get into this. Okay, so number one, we're going to have some math, okay? So everybody just sit down. There's no seat belts, so you can't really buckle in. But buckle in. I'm going to have to remember that one. But in all seriousness, I do want you all to be ready for that. So that's point one. Point two, some of this is going to be an Engineering 216 refresher, and some of this is going to be brand new. I'm going to do my best to take it one step at a time without this becoming a math lecture. So, tell me if I'm going too slow or too fast. But again, I'm not going to one thing I will say, I'm not going to make you derive this on a test. So don't worry about that, okay? All right, so beams buckle. When they buckle, there's an element of torsion involved in their response. So we need to talk about torsion. Now, unlike circular shafts, I-beams respond to torsion in two fashions. They respond through what's called pure torsion and what's called warping. Now, when I taught Engineering 216, and I've had a few of you had me for mechanics of deformable bodies, you'll remember that when we discussed torsion in that class, we never discussed torsion of things that were non-circular. It was either solid circular shafts or it was pipes, okay? There's a very specific reason for that. Unlike circular shafts, things in torsion, things like I-beams or square shafts or anything like that, they tend to warp. Now, let me skip ahead a little bit. What do I mean by warping? If I have something that's non-circular and I apply a torsion to it, not only does it rotate, but what happens is it actually starts to deform in and out of the plane. Like if you notice I've got this I-beam and I'm twisting it, the flange actually goes in and out like that. Does everybody kind of see that? So in other words, like here would be an unwarped section and here's a warped section. The flanges actually rotate in and out of that axis. Make sense? Circular shafts don't do that. And that's why when you take a mechanics of deformable bodies class, you limit your torsion discussion to circular shafts. In fact, if you were a mechanical engineer and you were designing some element and its job was to only resist torsion, I would do my damnedest to make sure it was a circular shaft anyways, because they're the most efficient in responding to torsion. Okay, make sense? Now, when you all took mechanics of deformable bodies, I know for some of you it's been a while, but I promise you when you took the class, you did discuss twisting of circular shafts, right? And you probably remember a formula that the angle of twist was TL over GJ, or TL over G times I sub P. Probably remember it something like that, okay? Where T was your torque, or your moment that you're applying, L was the length of the shaft, G is that shear modulus, and then J is your polar moment of inertia. And I don't like using I sub P because for circles it's a polar moment of inertia, but if it's not circular, it's its own unique constant, which is why I call it J. In here, what I'm going to do is I'm going to express that as saying that the moment, that torsional moment, is GJ times the rate of twist, the change in the angle with respect to the length of the section. Okay, so rate of twist. All right, does that make sense? Okay, now that's pure torsion. That's literally just the section doing this number, just literally changing an angle. But again, if it's non-circular, that's not all it does. It also warps. Okay, so how are we going to handle that? Okay, well, if you look at the section before and after warping, most of the deformation really occurs in the flanges. The web doesn't really do a whole lot. The flange is what's really going in and out of the page. Okay, so we're going to focus all of our derivations and make our assumptions saying that all the warping happens in the flanges. Even though there's probably a little bit of warping that goes on in the web, it's not comparative. Okay. Now, ultimately, what we're going to try and do is we're going to try and relate the shear force in the flange to the warping moment. So there's going to be some weird math tricks I do here in a little bit, but bear with me. Okay. So if I look at one of the flanges, since I've got some deformation, I'm assuming I'm going to have some sort of shear force going on inside that flange. This is how I'm going to derive that. So my goal right now is to determine one of these shear forces. Well, I don't really know what the shear force is, but I do know that the section has rotated some, right? So if I know that it's kicked out some displacement u, and I say, well, okay, I've got this length and this height, I can sort of determine that angle. If I'm using small angle theory, I could just say that, was it just treating that angle as if it's UF divided by H over 2. Okay. Now keep in mind that angle is our variable. Okay. And what do I mean by that? Well, that angle of twist, that changes along the section. I mean, over here I don't have any angle change at all. Over here it's changing quite a bit. Okay. You with me on that? Okay. Now, so I'm proposing that use of F, I can relate that as H over 2 times this angle. Now, what might seem kind of weird is I'm just going to take the third derivative of that. Well, okay, feel like taking the third derivative? Go right ahead. Sure, go ahead, Dr. Mike, that's fine. Go ahead and take the third derivative. There's a very specific reason why I'm taking the third derivative, and you'll see that here in a second. But specifically, it relates to the shear, okay? Now, if I'm taking the third derivative, if I'm treating this as the variable, then this H over 2 is a constant, and I'm just factoring that out. Everybody with me so far? Okay. Now, why am I taking the third derivative? Well, you all remember from structural analysis that the second derivative is related to the moment, right? Second derivative of deflection is m over EI. Okay. Well, the third derivative is related to the shear. Okay. Everybody with me so far? All right. So I propose that the third derivative, this third derivative right here, is instead of being m over EI, it's v over EI, and the negative just comes from our sign convention. Okay. So if I set those two terms equal to one another, I can determine what the shear force in one of those flanges are. It's E times the moment of inertia of one of those flanges times half the height times that third derivative. Recognizing that moment, how do you calculate moment? It's just a force times a distance. So if you got a force couple, you folks who are in concrete should be well familiar with this, just a force times a distance, in this case h. So I propose that the warping moment, if before we had, if I go right here, here's a differential equation for the pure twist. Here's the differential equation right here for the warping twist. Just E times this constant in the parentheses times that third derivative. Now that constant is the moment of inertia of the flange times h squared over 2. Everything that's inside those parentheses is a characteristic of that I-beam. Okay? It's unique to that specific I-beam. You know, each I-beam is going to have a certain height, it's going to have certain flange dimensions, etc. Everything that's in those parentheses is very important. For warping, it has a very specific name. It's called a warping constant. Okay? I love that, right? So here's our Diffie-Q for warping. In fact, I want everybody to turn to table 1-1. You going to turn to table 1-1? You going to turn to table 1-1?
Come on, Will.
We got to use Diffie-Q. I'm in trouble.
Oh, wow. It's already tabulated, don't you?
Down to your both in class. And it's a Friday.
Oh. Now, if you notice in table 1-1, you'll notice that there's a listing for J quantities and C sub W quantities, right? Now, those C sub W quantities they probably look a little ridiculous, right? They're like 580,000 inches to the sixth or something like that, right? What's that? They're large, yes. That just comes from the derivation. I mean, a lot of people one of the common questions I get is, what does inches to the sixth mean? Well, I remember when I taught mechanics of deformable bodies and I first showed students a moment of inertia, and they go, well, what does inches to the fourth mean? Well, I think it's just really, the units don't really matter. It's really more of a magnitude measurement. The larger your I value, the more stiff a section is in flexure. Well, the larger a warping constant, the more stiff a section is in response to warping. That's basically really all the behavioral interpretations you really need to make, unless you're starting to go into the world of stability and trying to do research on the stuff. We could have more in-depth discussions on things. Everybody with me so far? Okay. So what I'm proposing is that for torsion, we've got two different components, a pure torsion and we've got a warping torsion. Okay. Now the pure torsion is GJ times the rate of twist. The warping torsion is ECW times the rate of twist, but the third derivative because we're relating it to that shear in the flange. Everybody good? G is the shear modulus. It's E. If you want to compute it, you would take E and divide it by the quantity 2 times 1 plus Poisson's ratio. Did you all do that when you took deformable? I know we did.
That sounds familiar.
Let's see. No. And honestly, this is really more the theoretical discussion. We have some ways of getting around actually needing G, but if you want another simple definition, G is a material property for steel, just like E is. Okay, E is 29,000 KSI for steel. Period. G is a particular quantity related to steel. It is it's about 11,200, something like that, KSI, when you go through and do the math. So don't worry, I'm not gonna. That isn't one of those problem 1, exam 3, problem 1 questions. So don't worry about that. But Poisson's ratio in the V, that's about 0.3. That's usually taken as 0.3 for steel. Yes.
So you're saying that the third derivative relates to moment?
No, third derivative relates to shear.
Shear, yeah. So then it relates to shear in the second moment.
Yeah.
I thought like the first derivative relates to shear, and the second one is
If you're going back, if you're going the other way, if you go, all right, so if you start at deformation, okay, your first derivative is your rate of deformation, okay? So if it's deflections, then your first derivative is the slope, okay? Then your second derivative gets you back to moment. Your third derivative gets you to shear, and your fourth derivative gets you back to the loads. So it's, deformation, let's say slope, moment, shear, load. What you're talking about is just going the other way, starting at loads and then saying, well, your first derivative of your loads, that'll get you to shear, and then that'll get you to moment, etc. That's going the other way. You're talking about the relationship to go from load to shear diagram and shear diagram to moment diagram. It's the same relationship, just going backwards. But you're right. Well, we're using that relation. That's why we go a lot to a little. Remember that? Because we're essentially following that change. So a lot to a little. Because think our shear diagram is linear, let's say if we got a uniformly distributed load, but our moment diagram is parabolic. So we are using that relationship. Make sense? Yes? Yeah. Yeah. But a couple things. Number one, actually, I'll answer this 3 ways. Number one, this is more for explanation purposes. I'd say very rarely in a practical setting would you really need to derive a differential equation. That's number one. Number two, if you go to Chapter F, there are we're using the section in Chapter F for I-beams, and we're going to look at that here in a second. But for angles or channels or something like that, there are separate sections. So there are sections. Okay, so if you're dealing with an angle or something like that, just go to a different section of the spec. That's point 2. Point 3. Remember those design guides I mentioned earlier? Remember that design guide 3? It was like serviceability considerations for buildings. Well, design guide 9 is on torsion, and it's everything you'd want to know, or everything you'd need in most practical settings. So, again, I'd recommend downloading it. I mean, it's like those design guides, if you were to go and purchase them, would be a lot, like a lot of money, and they're free. So, sound good? Okay, is everybody with me on this? Everybody with me on this? Okay. All right. Let me erase my little equation. What time is it? Okay, this is what we're going to do, because the last thing I want to do is load you down with a bunch of differential equations. We're actually a little bit farther ahead than where I wanted to be, so I'm actually happy with that. This time we're going to do this. Tomorrow, or on Monday, we are going to fully derive our LTB expression, and then we're going to discuss how the code handles lateral torsional buckling, and ultimately how we can analyze and design for it. Okay? So really what I'm interested in you all taking away from today is the fact that I-beams have, or anything that's non-circular, has 2 responses for torsion. It has a pure torsion response and a warping torsion response. If we were dealing with a circular shaft, then this term over here would be 0, and we would just have GJ times phi prime. Okay? Just a heads up, in future derivations, because I'm lazy, I'm not going to write out the full derivatives. I'm just going to say like phi prime or phi triple prime or something like that, because I'm lazy. Plus, I think it makes it a little easier to follow. Sound good? Next time, we're going to carry out our full derivation and go from there, and then we'll do some discussion. But again, on Monday, be prepared for a little bit more math. All right, that's all I got for you all for today. If you're not in concrete, have a great weekend.